Okay guys, welcome back to the video. Today we are going to look at well order principle. In the previous video, I give you property of integers and trichotomy law of integers. Today we will have new property of integer which is well ordering principle. Now take a look at the statement of this. Well ordering principle which is P8. So let S be a subset of set of natural integer, and S is not an empty set. Then there exists an element x in set S such that x is less than or equal to a for every element in set S, for every a in set S. What does it mean by this? What does it mean? The meaning is that there must be a minimum element in every subset of natural number. So take a look at this note. Well ordering principle in the system of integer lead us to many theorem involving integers. Okay. Next one is the well ordering principle state that any subset of set of natural number has a minimum element. So let me rewrite this again. So if we have subset of set of natural number that is not empty set, then you will find an element in set S such that x is less than or equal to a for every a is in set S. Okay, for every element in set S. Okay, that means that any subset of a set of negative of positive integer that is not empty set always has minimum element. Okay, for example, you may have this set, suppose that it is set S, and you select subset of a set of natural number. You may have 5, 10, 15, 20, and all the way and so on. And we know that this is a subset of a set of natural number, and it always has minimum element. Okay, so this is the meaning of well ordering principle. So now we will use well ordering principle to prove the following theorem here. There is no integer between 0 and 1. It is well known that there is no integer between 0 and 1. Okay, but we are going to prove it by using well ordering principle. But how can we prove it? The way to prove this is I will let T to be this set, let T to be a set of integer such that this integer is between 0 and 1. Okay, we're gonna have this set, and then I'm gonna use the proof by a contradiction. So I have to suppose that there is an integer between 0 and 1. Okay, what does it mean by this? This means that T is not empty set. So you must be able to find an integer in this set T. And then since we have integer that is greater than 0 and less than 1, so if you have an integer that is greater than 0, okay, with this assumption, T must be a subset of natural number because you have integer that is greater than 0. So t must be a subset of a set of positive integer. Okay, so from this right here, we will use Weyl ordering principle. So by Weyl ordering principle, what do we have? So there exists, okay, element x in T such that x is less than or equal to m, and x must be the smallest one. So for all m in set T, okay, this means that x is this is minimum element in set T. Okay, so what does it mean by this? When x is in T and it is the smallest one, so we gotta have x being an integer, okay, such that x is between 0 and 1. Because x is in the set, so x must satisfy this inequality. So x must be greater than 0 and 1. Then, what do we have here? Okay, since x is an integer, what is x squared? Then we gotta have x squared. So a number that is less than 1 and greater than 0, and you square it, it gets smaller. So it must be less than x, right? Okay. And we know that x is less than 1, so it's going to be less than 1. And the positive number that is square must be greater than 0. Okay? And integer square turns out to be an integer. Okay? It turns out to be an integer. Alright? So what do we have again? X squared greater than 0 and less than 1, and it is integer. So it satisfies this condition. This means that x squared must be in T. So we must have x squared in set T. Okay? And x squared less than x. But x is the smallest element in set T. So we have a contradiction. Okay? So we have a contradiction, which is a contradiction to x being a minimum element in T. Okay? So this assumption right here is false, right? So this set does not exist. This means that T is empty set. Okay? So consequently, there is no integer between 0 and 1. Okay, so this is how to prove there is no integer between 0 and 1. Okay, so we finished the proof already. In the next video, I'm going to prove this Archimedean property, stating that for any positive integer a and b, there exists a positive integer n such that n times a is greater than or equal to b. Okay, so that's it for this video.